Hello everyone. The previous video I think was pretty well received. There was quite a lot of healthy discussion, and so I think we shall stick to this format for a little bit. We're going to present a series of questions on the same topic and just discuss some of them and leave some of them for you to figure out on your own. And this is really the spirit of Olympiads, right? Someone has to tell you something, but also some part of it has to be figured out by yourself. We're going to be dealing with the very notorious, especially at SMO junior senior level, topic which is basically variously known as roots, radicals, or surds. Those very annoying stuff. And I'm just going to show you some nice questions. There are questions that are simply not nice. There are ways to just have boring square root questions. There are also plenty of fun ones, which we shall try to appreciate from here. Oops. So, the first one is what I like to call a common trick. It's one of the first things that you want to look out for, which is that when the square roots look too weird, sometimes the question is not meant to be difficult, you're just meant to notice, well, something. Can you tell what that is? So if you took a glance, I think the thing that stands out is this guy here. Now, basically when things look very weird, they are probably meant to be weird. As math Olympians, part of your job is always to know that these questions can be solved in a few minutes. This is not a research level question. This is not an IMO level question even. So it should be solvable in a few minutes, and usually you just need to find something to break into the problem. The number one property about square roots is that square roots of negative numbers do not exist in the real world, and the real world meaning the world of reals. So both of these have to be greater than or equals to 0. They are negatives of each other, which means that they are both 0. Which means that x squared equals to 4, and that means that x equals to square root of 4 equals to 2. Right? No, not right. That is not right. So the square root cannot be of a negative number, is one side of the coin. The other side of the coin is that if you have got both sides being, let's say, x squared equals to something and you square root them, there is always a plus or minus. Now, the x squared equals to 4 does not mean x is square root of 4. It is plus or minus the square root of 4. And so therefore, if you try to put in x equals to 2, you get gibberish. If you put in x equals to minus 2, then you are left with, well, this thing will be 0. So you're left with s is 3 to the power of 2017. Last digit questions is a topic for another day, so I shall just leave the answer to be there. And if anyone does not know how to deal with last digit questions, please ask in the comments below. I'm sure someone will be happy to help you. Second question and second idea is computing roots. Now, usually we cannot compute roots. This is not a secret. This is just like trigo of non-special angles or logarithms. We are not calculators. But we are humans, and humans are smart enough to do some things without a calculator. Now, here I'm telling you that the answer is a positive integer. What would you say is the fastest way to do something like this? Now pause the video for here as well as any of the subsequent questions if you want to think about it for a little while. I would say that for this one, the number one thing I want to do first is to just figure out the number of digits. Right? So first of all, 100 cubed is a million. This is 2 point something million, so it's more than 100. And obviously less than 1,000. So if it's 3 digits, I can just start by getting the first digit, and 200 cubed is already 8 million. So this is between 100 and a 200 values, so it's 100 and something. Now, to get the second digit, the 10th digit, I would say that you can kind of use a quasi-binary search. Basically just use multiples of 10 to get the second digit. And this requires you to calculate 15 cubed. That would be 3375. So this is smaller than 150. And then if let's say that you went for something in the middle, like 130 cubed, which means you need to calculate 13 cubed, you get 2197 with 3 zeros behind. So it's between 130 and 150. If you went for 140, you get this. So if you knew what 13, 14 and 15 cubed beforehand, it would not be too hard for you to know that the second digit is a 3. Now, for the last digit, you look at the last digit. So what cubed can give you a 7? Sorry, give you a 3. I said out the answer by accident, didn't I? What cube gives you a 3 that's a 7? Now, a fun property of cubes is that all the last digits are different, right? So 1, 8, 27, 64, 125, 216, 343, 512, 729, and of course the last one will be a 0, which is probably not even on your radar, but all the things from 1 to 9 and 0 are here. So therefore, you can always get the last digit immediately. This is different from, let's say, square root or even a fourth root, where there may be a few different ways where the fourth power ends in 1. So the answer is 137. That was not too bad. The next task is solving equations, and there are plenty of really boring equations to solve, but let's look at a slightly more interesting one. Once again, feel free to pause the video to think about this. What would be the easiest way to deal with an equation like this? The square root of 3x minus 47 plus the square root of x minus 1 equals to 6. So for many of these equations, previously did a video a couple of years back called zooming in and out. You often want to look at the equation and just take a moment to zoom out and see if anything special can be found. That special feature, unfortunately, is impossible to come out from a list. It just comes from experience, and the more problems you do, the more you look at these sorts of equations, the more special things you know how to look out for. And here, the thing that you can look out for is that this is an increasing function in x. Meaning that if it's increasing in x, as x gets bigger, the left-hand side gets bigger, there should only be one solution. There will not be more than one solution, and so all you need to do is to guess. If you want to guess, we know that the SMO answers are whole numbers, so you can guess by just trying to make, let's say, square root of x minus 1 be integer, as well as the fact that you have to start from the fact that this is not negative. So the smallest thing you could start from is 16. not much luck there, but if you go to 17, that's your answer. Now, many of you often will complain that there is not enough time in Olympiads. I'm absolutely in concurrence with the fact that there is not a lot of time in Olympiads, but very often there will be a mix of questions that cause you to drain time and questions that will allow you to buy time. Now, a question like this allows you to buy some time to bash some ugly geometry or algebra or counting question somewhere else. Next up, nested surds or nested roots. Don't be too bothered about the preamble in the question. I included this just to remind everyone that as we get into Olympiad season, there is always this answer extraction issue where they want to make sure that the final answer is an integer, and so they have to specify it very precisely, but also giving you a very unnecessarily long problem statement. Basically, solve this equation will do. There are nested roots here. Think for a moment, what would we want to do to get rid of them? Now, a common trick is to just substitute away any square root that we don't like. We can't substitute too many square roots away because all we have done is just replace the entire equation by 3 new variables. But if it's just one of them that's recurring, why not? Y equals to square root x plus 1 means that y squared is x plus 1. So 4x plus 5 is 4y squared plus 1. And x plus 2 is y squared plus 1. So of course these are both squares. Which means that if I remove the square roots, I just get y equals to 1. And that's a bit silly because that means that the answer is 2. It's just 1 over 1, so answer is 2. No, that's wrong again, isn't it? We are back to the same thing again, which is, are you sure that you can square root the square like this? We have a missing absolute value, so can't celebrate too prematurely yet. This is actually the equation that we should be dealing with. 2y minus 1 plus y minus 1, both in absolute value, sum to 1. Now, once you have that, this is not too hard. You will split into cases depending on which of these are positive. So, of course, we have already found that y equals to 1 is a solution. But what other solutions are there? You're going to find that there's also y equals to 1/3 that satisfies the equation. And so therefore the answer is not 1, the answer is 4. This is a video where we're talking about square root, so once again, I am not going to talk too much about the mechanics of solving this. If anyone has any issues with solving modulus equations, once again, I'm sure someone else in the comment section is more than happy to help you out. Let's add more square roots instead. This video is about square roots, so I cannot shortchange you. Here are more square roots. Now there are 4 of them. Well, there were 4 of them just now in total, but there were 2 sets of 2, so now we have got 4 of them layered together. Now, from 2 years ago, when I recorded this review of that year's SMO Open, now I review the SMO Open paper usually and all the SMOs pretty much on the same day or the day after, so I just do the first thing that comes to mind. That should probably be the first thing that comes to your mind as well when you're doing an SMO question, right? As long as I have a method that works and will not take too long, I shall just do it. The thing that comes to your mind first is what you should try, but that does not mean that it was the best solution. And so with some thought and also with some suggestions from elsewhere, I realized that we can do this a bit better, and that would also make it fit very nicely into this video. The idea being that you can do a self-substitution and hence I said even more nested roots. And then you can substitute again and again, and basically this is going to just become an infinite series of roots. And from it being an infinite series of roots, we can come back down again and say that, oh, this whole thing is t, but this whole thing here is also t. And so from having 4 layers, you have now dropped down to 1 layer. T equals to square root of 1 plus t, and you can solve this fairly easily. In fact, this is our ubiquitous golden ratio. So it's pretty nice. Right, t to the 4. In fact, is equal to t cubed plus t squared is how you can arrange this. And so this would cancel to t squared, and then t squared minus t will cancel to 1. So your answer is 11. Now we carry on to a pretty well-known idea that is actually not that easy to prove. Okay, so square root x plus square root y equals to the square root of 20240. I'm going to present the solution without a rigorous proof, but I will leave it to you to suggest what the rigorous proof is. Square root x plus square root y is square root 20240. The way that we do it is to first simplify the square root as much as we can. Now, you probably know the factorization of 2024 by now from the previous video. So 2 cubed, you can take out 1 more 2. And now you have got 2 squared taken out. And I think this is what it should give you. You have 4 square root 1265. Now the claim is that once you have pulled out as much as you can out of the square root x and square root y are going to just share some number of copies of the square root 1265. So 1 and 3, or 2 each, or 3 and 1. Now, this is the correct answer. I am not lying to you unless I have multiplied something wrongly, but this should be the correct answer. It is not hard to see that all of these do give you valid x and y. The challenge is for you to figure out, how do we know there is nothing else? Now, to end off, we're going to ask a very suggestive looking question. How many positive integers x less than 2024, meaning 1 to 2023, satisfy x cubed is congruent to 1000 modulo 2024? Now, obviously, we all can see the one value that will work, right? X is 10. The question that is not so clear is, how do roots work? Can I cube root both sides in modulo arithmetic? I'm going to say straight up that the answer is not 1. That means that there is something else other than x equals to 10. And that's because in modular arithmetic, everything can work, but not exactly in the same way. You have already got a factorization just now. I'm not going to belabor that. So I'm going to kind of split this open first. We have got x cubed is now supposed to be congruent to 1000 mod 8. X cubed is congruent to 1000 mod 11. And x cubed is congruent to 1000 modulo 23. Do these actually still work the same way as we would expect? You're going to see that, of course, I can reduce all of these down. Numerically. For this one, if x cubed is a multiple of 8, x just needs to be even, so it's just 0 mod 2. For this one, if x cubed is congruent to 1000 mod 11, which is negative 1, if you just listed out all the possibilities, you're going to just end up with, well, there is only one possibility, which x is actually negative 1 mod 11 or 10 mod 11 if we want not to be excessively fancy. We know that 10 works, so 10 works there. This is actually the only solution for mod 11, and likewise for mod 23. It turns out that these are the only ones that work, which means that I can combine them back into x is 10 modulo their product, which is not 2024. It is modulo 506, which implies that there are 4 solutions. Now, over to you to kind of think about another question, which is just going to be one number away, but potentially look a bit different. Now, how about x cubed being congruent to 1000 modulo 2023? There's a difference, and for most of you, I would urge you to just try to figure out the answer. For a few of you, you can also think a little bit more deeply about when are cube roots going to be unique, and when are cube roots not going to exist, and when are cube roots going to be non-unique. I'm going to leave it here. There are quite a lot of hanging questions for you, and I think this is the spirit of Math Olympiads, right? Questions can never be answered in full, but I hope I have proposed some good ideas and some good questions. Let me know if you have any other follow-up questions, and look out in the comment section below, where I'll probably get around to answering this if nobody figures it out. So thanks for watching. See you again next time.